Welcome back, everyone. This is our second video in the series for section 3.1, quadratic functions. Yesterday, we understood the distinction then between the general form and the standard form of the quadratic function. We reviewed the parent function and its characteristics. And we determined that for the graph of a parabola, it is a much better idea to have our hands around the standard form of the equation. We reviewed how to transform using vertex form to get to h and k, where h is the opposite of b over 2a, and that the k value is simply f of h, where we plug back into the original equation. We also completed the square, understanding that the x minus h quantity squared is a perfect square trinomial, and we've been intentional to express it as a binomial square. We said that that helped us to sketch by hand. We would know if a was greater than 0, the parabola opens up. If a is less than 0, the parabola opens down. We also can, once we found h and k, we can locate that vertex. We'll know whether it's a min or a max. And we also then can discern that x equals h, that line of symmetry. One more layer then are the intercepts. We worked very, very hard in chapter 2 when we were discussing quadratic equations, and we were solving them. We were finding solutions. We were finding zeros, and we said that real zeros are x-intercepts. Real zeros are x-intercepts. In other words, this is where that curve is going to cross. And when we solved equations, we had really three options. And if you recall, we evaluated in quad formula the b squared minus 4ac. And we said if it was greater than 0, there were two x-intercepts. And if b squared minus 4ac equals 0, there would be one x-intercept because we had a PST. And we said if b squared minus 4ac was less than 0, while we had two algebraic zeros, they were complex. So we had no x-intercepts. This kind of information then is going to be important when we go to graph. What are we looking for? What are we expecting? Sometimes our curves are going to cross in two places. Sometimes our curves are only going to intercept in one place, and sometimes our parabolas aren't going to have any x-intercepts at all. Now you may recall when we talk about a zero is a solution to the equation f of x equals 0. Because let's think about that for a second. When we talk about the x-axis, isn't it true that every single point on the x-axis always has a y value equal to 0? So again, I'm looking for these a's, if you will, the values of x in these ordered pairs that when plugged back into the original equation would yield a 0 in the y value, and that's why they're called zeros. So today I'm going to draw your attention back into the textbook to page 248, example number 3. We're going to talk a little bit about how to find zeros as a quick reminder, because we've really done this, and then really talk about what that means. So again, example number 3 on page 248. In this case, I have f of x equaling the opposite of x squared plus 6x minus 8. Well, if we're asked to find the zeros, aka the x-intercepts, or perhaps complex zeros, which aren't x-intercepts, but algebraically, if we're asked to find the zeros, we're going to set f of x equal to 0 and solve, which means if I'm delivered anything other than all terms on one side and 0 on the other, the first thing I have to do is manipulate the equation to get all terms on one side and the 0 on the other. The other thing is, you know how I feel about a lead coefficient that's negative. Blech, don't like that. So effectively, we're going to ask you to divide both sides by -1, all terms, both sides. In doing so, all we've done is change the sign of each of the terms. This one's factorable. Like that, factor wherever we can, trial and error. The coefficient is a 1. Third term is an 8. I'm dealing with 1 and 8, or 2 and 4. Oh, by the way, these better both be negative, because what? Negative times negative is positive, but negative plus negative is just more negative. So now I have x minus 4, x minus 2. Zero product property says that this is true if and only if one or both of the factors equals 0. X equals 4 and x equals 2. So now I have additional information. I know for a fact that I have an x-intercept of my parabola at 4, 0, and I also have an x-intercept of my parabola at 2, 0. Factor, 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 whenever you can. If all else fails, you certainly can use what? Quadratic formula, but oftentimes we'll be able to factor. And if that's the case, then let's go for it. Let's see if we can't finish our information now. Let's do a transformation. This is not specifically in your text, so follow with me. Let's finish off. What else has gone on with this particular parabola? Let's use the vertex form to find the vertex. So we've got a equals negative 1, b equaling 6, and c equaling negative 8. Well, h is going to be what? The opposite of b over 2a. So that's going to be negative 6 over 2 times negative 1. Well, that's negative 6 over negative 2, therefore h is 3. That's the x value of the vertex. It also tells me that the line of symmetry is going to be x equals 3. To find the y value of the vertex, then we're going to evaluate f of h, or f of 3. So this is negative 1 times 3 squared plus 6 times 3 minus 8. When I simplify that, I get a 1. So I know that the vertex for this parabola is at 3, 1. I know that the line of sim is x equals 3. A is less than 0. This opens down. And I've got x-intercepts at 4, 0, and 2, 0. I should be able to plot this and connect the dots. I can sketch this easily now by hand. So again, I've just completed example number 3, taken it further than the book by doing the whole job. If you take a look at 3.4, figure 3.4 on page 248, you'll notice the vertex is at 3, 1. The x-intercepts are at 4, 0, and 2, 0. Now, moving on to example number 4. Sometimes the given information doesn't include the equation. What to do then? What if we're given 2 solution points and we're not given the equation, and yet we've been asked in example 4 to write the equation of the parabola? So we're going to do our work a little bit differently. Again, we can only work within the framework of the 2 forms of the equation that we know, the general equation or the standard form. My preference is the standard form, based upon the information that's been provided in the problem, together with the fact that if I've been asked to sketch without the use of my calculator, I need to have all of these clues, all of this information in order to complete that sketch anyway. So again, I draw your attention to example number 4. And it says, write the standard form. Standard form of the equation of the parabola whose vertex is 1, 2, and passes through 3, negative 6. So again, example number 4. So let's extract information from the example that's helpful. First of all, they want standard form. That's the goal. So that's f of x equals a times x minus h quantity squared plus k. You might notice this is very similar to the equation of the circle, but it's not exactly the same. It's similar, but it's not exactly the same. You memorized that equation when we were working with circles. You're going to need to memorize this formula as well. So given information this time, they told us in the problem that vertex which we know as hk, is equal to 1, 2. They also told us that there was a solution point. In other words, another point on the curve besides the vertex. And I'm going to be intentional. I'm not going to call it xy this time. I'm going to call it x, comma, f of x, because we know that that's just a notation change, but because we're working with functions, please use the f of x reference. Specifically, that ordered pair, that solution point provided in the problem is 3, negative 6. Now, I have one equation, which in theory I have 1, 2, 3, 4, 5 unknowns. This is an impossible scenario because in algebra, for every unknown that you have, for every variable that you're seeking to find, you need to have an equation. You've noticed when we were working in doing our intersections in the last chapter, we had a system of 2 equations when we were solving for 2 unknowns. So here, in theory, if I knew nothing, I would have to have 5 equations that somehow or another related to one another so that I might unpack all that I needed to find. But the news is good. The given information in this problem has provided for me 4 of the 5 unknowns. So if I'm given a problem and it's in this format, if it's set up this way, here's what I know. I have h, I have k, I have x, and I have f of x. The only one that's really missing here is a. So if I'm given information like this, I solve for a. So let's plug in what we know and solve for what we don't. So f of x is the y value, that's at negative 6. The a we do not know. The x is 3. The h is 1 squared. The k is 2. So literally all I have done is I have modeled this standard form plugging in the given information. Now let's solve for a. Well, 3 minus 1 is 2. Of course, that's squared times a plus 2. And this is all going to be equal to negative 6. Now negative 6 is going to equal 4a plus 2. Subtracting 2 from both sides, I'm now at negative 8 equals 4a, dividing by 4 on both sides, negative 2 equaling a. So now I've figured out that I have a negative a value, which means I have a reflection with respect to the x-axis. I still have a vertical stretch by a factor of 2, but of course I'm going in the opposing direction. Now the problem says, okay, put it all back together, give this to me in the standard form. So my final answer, I'm going to revert back to x and f of x because it needs to work for any point on this particular curve. So I'm going to revert back to using the notation f of x. But in place of a, I now know I have negative 2. I'm going to use x as prescribed, but the h is positive 1, and this is a subtraction pattern, so minus 1, and we're squaring, and the k value is a positive 2. So we have now taken 2 points, the vertex and a solution point, and together we now have the standard form of the equation of this parabola. I now ask you to again go back to page 250 with me, please. And we're going to pick up at number 31. I want you to take a look at the directions at number 31. It says, identify vertex and x-intercepts. Give the description of the graph. The work that we've done today will allow you to do that. Moving forward, 37 and 38, same kind of information, only this time it's been given to you as the graph, and you are to find the equation. Last but not least, numbers 39 through 44, they've given you this kind of information. This is a slightly different, again, version, but they've given us the vertex and they've given us a solution point, and you have to come back and give the equation. So please use example 4 to help you do numbers 39 through 44. And then finally, got some graphs again for you to look at, numbers 45 through 48. This time it says determine the x-intercepts of the graph visually. So we're literally looking at the scaling on the x-axis, determining where the curve is crossing the x-axis, and coming up with the associated ordered pairs. I expect now that you should be able to complete the assignment up through number 48. Again, it's due this evening, the 24th, by 9 o'clock.